This week's lab topic is on density. We will be determining the density of both a liquid and a solid. We know that one of the fundamental properties of any sample of matter is its density, and we define density simply to be that unique property that every sample of matter possesses, measured by taking a ratio of mass per unit volume. Mass per unit volume. To determine the density of a sample of matter, there will be two measurements that we need to take, the mass and the volume. And the purpose of our experiment is to indeed determine the density of an unknown liquid and that of a solid. To remind ourselves mathematically, density is equal to the mass per unit volume. Sometimes a little algebra tool I call the round little buddy. And if I display the algebraic relationship between mass and unit volume, I come up with the term density. We know that mass is typically measured in a unit called grams. Volume can be measured either in a milliliter or a cubic centimeter, because we know they are indeed the same. A milliliter is indeed the same as a cubic centimeter when measuring with water with its density of 1. So for most common purposes, we interchange those two units. And density, of course, would be the derived unit of gram per cubic centimeter or gram per milliliter. In our experiment, we will be using gram per cubic centimeter to denote the units on density. Now, the way the round little buddy works, I just simply cover up the variable. In other words, if I'm solving for density, I cover that up with my hand or my finger, and I can see m divided by v becomes my formula. If I'd like to know volume, that's the variable I'm covering, and I can see the ratio of m over d. And if I'm solving for mass, it's the variable I cover, and d times v becomes my algebraic formula. Density is defined as mass per unit volume. We do have three components of our experiment, a part A, part B, and part C. The part A of our experimental procedure has a learning goal that has us practicing really just becoming proficient at using the analytical balance, both to master both precision and accuracy. Precision: am I able to repeat the experiment over and over and get a concise answer? And with the term accuracy, am I coming very close to the correct answer? So in a general speaking, mass of coin 1, I'm going to take a penny and I'm going to place it onto an analytical balance, and I'll get a measurement. And I have no idea, but let's just make up a value. I'm going to say that it comes out to be 1.5099 grams. I have no idea if I'm close. I'm making that number up. I put the first penny aside, and I place a second penny up there. And let's suppose its mass is coming to be 1.5100 grams. I then take both pennies off and put them both back on, and just zero the scale between to make sure that you're starting at 0. If I mass both coins together, let's suppose I get 3 is 1.5 and 1.5 is 3, and then I'll say 2010 grams. That's both pennies sitting on there. Let's make a statement how close that accurate value is by taking the sum of penny 1, again a made-up number, with the sum of penny 2, and what would that denote to be? Carry my 1, 3.0099. If the sum of those two is far different than my calculated average, if I take these two and add them and get a very different answer than this, I want you to start over. I was not very precise. And you'd be surprised, it really does just take practice in getting the analytical scale skills that we need to be proficient chemists in the lab. So again, overall purpose, we're illustrating what's called the law of conservation of mass, where the sum of both reactants should equal the product. I want you to show yourself that you can mass two separate pennies then place them both on the scale and get an answer that's close or very, why not the same? Let's aim big, as the sum of individual pennies added together. The weight of the scale, when both coins are on, should indeed be identical to when I'm adding individual weights together. The law of conservation of mass. But really, it's just a sneaky way to get you to practice your skills at being precise and accurate when using an analytical balance. Let's talk about part B of our experiment. Here we are determining the density of an unknown liquid. We are going to start by using a flask, and a flask really is just a round bottom, and we might be using an Erlenmeyer. Sometimes I'm not a very good artist. We could be using a volumetric flask, but it's a round bottom flask, or a vessel that allows us to measure the volume of a trapped amount of liquid. So one of the things that we'll have us do is to take this empty flask that's very clean, very dry, and we're going to stopper it with a piece of glass up on the top. So we're going to stopper it up, and we're going to weigh it on the scale. And when we weigh an empty flask and record its mass using the analytical balance that we just practiced from part A, we're going to get a very precise amount of a weight or a mass of an empty flask. And I'm just reading through our pre-lab or our advanced study assignment to find my made-up values here. So step 1 of our advanced study says, let's just go weigh an empty flask after I've cleaned it, and the weight of that empty flask is given to me in my pre-lab data as 32.634 grams, provided from just simply placing an empty flask, all stoppered up, clean and dry, up on our scale, and just simply record what it says. Then I simply take the flask and I take it off the scale, open it up, remove the stopper, and I'm going to fill it to the tippy top with water, so that when I replace the lid here, it's even going to overspill. We do not want any air gap in this flask at all. We want it to be completely filled with water. When I completely fill it with water and I make sure that the outside is dry, water drops are very heavy. We want to be sure that it's completely dry on the outside so we don't have any clinging added weight. And I plunk it up on the scale again. This time it says we have a mass of 59.479 grams. If I know the empty flask and I know the flask with the water in, we're looking at a simple subtraction, aren't we? How much does the water weigh? Well, if the flask indeed weighs 59.479 grams when it contains the water, let's subtract the clean flask, and that's a 4. Just carrying that down from here. And we're going to find the weight. Hit it on your calculator. Make sure we get a common answer. Find 59.479 and subtract out 32.634. Did you find 26.845 grams? And what that is the mass of our water. How much water can this vessel contain? Alrighty. Now it also says that using charts, and I just looked on the internet, we can find the density of water at a specific temperature. We've probably learned that the density of water is 1 gram per cubic centimeter or 1 gram per mil, but technically that's true at a very specific temperature. At 4 degrees Celsius, which is pretty chilly, water freezes at 0 Celsius. Water does indeed have a density of 1. But typically room temperature and the temperature of our lab is closer to 25 degrees Celsius. And you can see the density decreased slightly from 1 gram per cc to 0.997 grams per cubic centimeter. If that is indeed the given density, and we know the mass, we're being asked to solve for the volume. Remember your round little buddy? If mass over volume is density, we know the mass of the water, right here, 26.845, and we know the density of the water, right here, 0.9970. Our target variable is the volume. So how do we pull out volume from that equation? You got it. It's mass divided by density. And that's indeed what we'll hit for that particular question. We're going to solve by taking the grams. We measured 26.845 grams of water. And we're going to divide that by the density provided for us, 0.9970 cubic. Oops, that's gram per cubic centimeter on the density label. So on your calculator, your key sequence literally would be 26.845 divide by 0.9970. And what is the volume in a cubic centimeter? Hit it. Be sure I hit it correctly. Make sure we get a common answer. $26.845 divide by 0.9973. My calculator is saying 26.918 cubic centimeters. And there's your volume right over here, just simplified. 26.918 cubic centimeters. We determined the mass of the water experimentally by weighing an empty flask, filling it with water, and weighing it again. The difference must be the added weight there is the water. Knowing the density of water provided for us, we take the mass over density to pull out V, the volume of the flask. So far in our journey, sorry I coughed, we have now determined the size of the flask, how much volume the flask contains. So every time from now on, we know the size of that flask. It's 26.918 cc's, cubic centimeters. Now the problem goes on, and they're looking at more of a letter B. It says, okay, empty the flask again, make sure it's clean and dry, and what we now want to do is to fill it with our unknown liquid. You're going to be given a liquid. It's going to be labeled unknown 1, 2, 3, or 4, and it will be brightly colored depending on the sample that you're taking. I'm going to fill that flask completely with this unknown liquid. So instead of filling it with water as we just have done, we're now filling the empty flask, fill it all the way full with this brightly colored solution labeled unknown 1, 2, 3, or 4. I'm going to stopper that again to be sure there's no air gaps. That's the critical part. I don't want any empty space in there. So I fill it so full that even when I put the lid on, it's going to overspill a little bit. And I weigh it again. Now reading your pre-lab, this is the number 2, page 11. How much does it say it weighs? We've obtained the volume of the flask, we fill it with this unknown, and the value that I see from my pre-lab is that now it's weighing 50.376 grams. So this brightly colored solution in the flask is 50.376. Well, if we ultimately want to calculate its density, we better figure out the mass of that solution. So right up here, we know the mass of an empty flask. Remember that? We calculated 32.634, just the weight as it sat empty. Why don't we subtract the empty flask from the mass of the flask with our unknown solution? So here's the mass with this brightly colored solution in it sitting on the scale. Let's get rid of the empty weight and see the difference. The difference in mass must be the actual solution. So on my calculator, 50.376 minus 32.634, and this mass looks like 17.742 grams. To calculate density, we need the mass of our unknown solution. We just found it, 17.742 grams. We need to know its volume, but we have that. The volume of the flask we determined right here was 26.918 cubic centimeters. Solve that ratio and we have the density. The mass there, 17.742, divide by 26.918 cubic centimeters. And my screen is saying 0.659 gram per cubic centimeter. Here's the density of our unknown liquid. Now again, your numbers will be different, but the process will be the same during our experiment. Let's talk about the last part, Part C. This one had a title called Finding the Density of a Solid. So here we begin with our clean, dry flask. So you're emptied out the last solution. You're going to use air to actually dry the flask, add a little acetone rinse, and use the air to create a nice dry vessel to weigh. So again, I weigh and clean this thing. I'm going to fill it. It says about halfway full of a metal. So I'm looking for something like copper shot or mossy zinc, some sample of metal that I can place into this flask, and I'm going to just approximate halfway full. Alrighty? And I'm going to plunk it on the scale. How much does the flask and the metal weigh when the flask contains approximately half full of an unknown metal? Now as I read through my pre-lab, it says that when I weighed the flask and its contents, it weighed 152.047 grams. This is the metal and in the flask. The next thing it has us do is take that flask off of the scale, and I want you to fill it again to the tippy top with water. Just get a visual with me. If this is our flask, and I'm not the best drawer, especially with this program, we had a sample of matter, which was just these metal pieces in here, and we weighed it, 152.047. Next thing I'm going to do is fill all the rest of this picture with just fill it all the way up with water, stopper it up so that even the water overspills a little bit. I don't want any air pockets in there. So I have absolutely every spot is occupied either by the metal or by water. Shake it up a little bit. Be sure that there's no pockets of air even after shaking it gently. And I want you to weigh it again. When the flask is completely full with metal and water, our pre-lab now says it is weighing 165.541 grams. That's the flask, the stopper, the metal, and the water all component up in here. So how do we find the mass of the metal? Well, we know the mass of the metal was 152.047. How about the empty flask? Previous slide. Here it is, 32.634. That's just a flask all by itself. Let's get rid of that weight. 32.634. Flask with the metal, flask without the metal. That difference in weight must be the contribution of the metal, 119.413 grams. This right here, the mass of the metal I poured into the flask. Alrighty. Well, how much was the water weigh? Well, here we have the mass of everything, including the water, 165.541. Alrighty. What would we subtract to find just the mass of the water? Well, wouldn't we want this mass right here? 152.047. I know that comes out as a 9, but that's me dragging the pen on the slide here. 165.541 minus the flask and the metal. The only difference between these two lines in the data table is that of the water. So here's my mass of water, is that particular difference. 165.541. Subtract out 152.047, and my calculator is saying 13.494. What must be the volume of the water? Well, remember our density formula. Density is the ratio of mass per unit volume. If I'm looking for volume of the water, I'll rearrange my algebra, and we can see that it's found by taking mass over density. Previous slide. Remember what we called density of water? It was a given quantity, 0.9970. We're going to use that again here. Alrighty, so 0.9970 is my density. The mass of the water, I'll just rewrite that right here, 13.494. That's a point. The mass of the water divided by the density gives us the volume of the water. Hit that with me. What's 13.494? Divide out by 0.9973. Oops, why am I writing 0? Let me check that. 9970. I was wrong right here. Where did I make that mistake? Oh, I was right here. So I must have just misspoke when I said that. I was just checking my value. So I'm good. 9970. So, sorry, I was just checking to make sure I didn't make a calculator mistake. 13.531 cubic centimeters is the volume of the water. Ready? So now if I know the volume of the water, I know the volume of the entire flask, what must have been the volume of the metal? Alrighty. So thinking back, what was the volume of the flask? We solved for that. Remember right here, the volume of the flask, 26.918 cubic centimeters. That's going to be carried right here. So if 26.918 cubic centimeters was the size of the whole flask, let's subtract out what the water was contributing. Let me erase that. That was 13.531 cubic centimeters. So remind ourselves, this is the flask, the size we determined in the previous slide, minus the volume of the water we just determined, because the water and the metal would be equal to the entire flask. I'm just subtracting those two to see the difference. And that I'm finding to be 13.386 cubic centimeters. Alrighty. Do we have the two calculated numbers we need, don't we? We have mass of the metal and we have volume of the metal. What's the density? Density is determined by taking the mass of our metal and dividing it by the ratio of volume, 13.386 cubic centimeters. Hit it with me. Grams, 119.413. Divide by volume, 13.386. And I'm finding a density, very large number, 8.920 grams per cubic centimeter. What have we learned? We learned that part A of our experiment will be practicing the use of an analytical balance by trying to get a constant mass reading of pennies. Part B, we've learned how to determine the density of an unknown volume. And in Part C, we've learned how to determine the density of an unknown solid. And friends, there really will be correct answers when you turn your lab reports in. So practice the skills of being a good measurer. We want to create accuracy and precision so that you won't lose points on your lab report for turning in incorrect answers. So in other words, your calculations may be correct, but there is a correct, accurate answer. Aim for that. And we'll see you in lab.